Now let's look at a few more examples using finding probability using our normal curve and our calculators. Since the standard normal curve is the way that we standardize all populations that are approximately normally distributed, to connect the two together, we're using the z-score as our bridge from one set of data to the standardized curve. There are four basic types of probability problems that we looked at. Number one, the probability that it's less than some value. This means that the lower boundary on the left-hand side is going to be negative infinity, and then we're going to have some right-hand boundary that is static. Probability that it's greater than some value. So in that case, we have a lower boundary that's static, and then we have an upper boundary that's infinite. The probability that we have that we're finding an area between two values. And then we're also going to look at a probability when we are less than one value, which indicates our lower tail, and greater than another value, which is the right-hand tail. So let's apply this to an actual real-world data scenario. Body temperatures, we're told, are normally distributed with a mean temperature of 98.6 degrees Fahrenheit and a standard deviation of 0.73. What then is the probability of having a normal body temperature that's less than 96.9? Well, picturing this on the normal curve, we know that 96.9 is less than 98.6. So somewhere over here on the left, we're not exactly sure where, we know that we're going to be looking for an area that's less than this, and so we're going to be looking for a tail area. If we plug this into the z-score, or the z formula, we can find out exactly where this would be on the standard level curve, and it's at negative 2.33. If you're putting this into your calculator all at once, this is something I might have pointed out earlier, but you need to put parentheses around this top subtraction. Otherwise, you're never going to get the right outcome. Your calculator follows the order of operations, so it would actually do the division that you enter, which, if you don't put parentheses, is only under the second number. And so it's going to do the division first, and then it's going to subtract. But if you put parentheses around the subtraction, it will do that first, and then it will divide that difference by 0.73. So this is what you should get. So we see that on the standard normal curve, we would be over here, just to the left of negative 2. Using technology then, with this as our z value, we would go negative 1,000, comma, negative 2.33, our upper boundary, comma 0, comma 1, and we get 0.0099. Another way to do this without having to first figure out what the z value is to use normal CDF, but use our original data values over here. So again, negative infinity, we want to pick something that's significantly large in a negative direction, all the way up to negative 96.9. In this case, what would be extreme enough could even be 0, but the bigger you get, the more safe you are there. And then we put what the mean temperature was, which is the mean of my data set, 98.6. And instead of putting 1 for the standard deviation, we put what the actual standard deviation value is for the data set, which is 0.73. You see that this also gives us that same outcome. So we can use our original data values with our given mean and standard deviation. Therefore, we conclude that the probability that x would be less than 98.6 is 0.099 or 0.99%, which is barely less than 1% probability. It's highly recommended that as we look at the following scenarios, that you practice drawing a normal curve. You really need to get familiar with and feel comfortable with a normal curve, what area you're after, what the expectation can be for that area that you're after, and labeling your x-axis, which is the horizontal axis, with either your z values or your data values, and then shading the area described below as you use your technology. So here's our data set. We're talking about replacement time for CD players. with a mean of 7.1 years and a standard deviation of 1.4. First thing we want to find is that the probability that a randomly selected CD player will have a replacement time of less than 8 years. So draw a picture of this and see if you can calculate the probability that it would be less than 8 years. Pause is necessary. In probability notation, this is how we would write this. Notice that instead of z now, I'm putting x. X represents my data values. A z here would represent a z value. 8 is not a z value, it's a data value. It's referring to years. So we use x instead of z. So we say the probability that my randomly selected CD player would have a lifespan of less than 8 years. If you drew a picture, you'll notice with 7.1 at your center, 8 is definitely going to be over to its right. If we're going less than that, we can expect to get something before we even calculate, expect to get something that's greater than 50%. And we do, 0.7389. How about a replacement time of more than 9 years? When a pause is necessary. Probability that my randomly selected CD player is greater than 9 years is 0.0869. We can expect that by looking at our curve, not the exact 8.69%, but we can expect that it's going to be way less than 50%, way less than half, because 9, again, is to the right of 7.1 on our x-axis, and we're going greater than it. So that means we're in the tail region, and that's what you should have shaded on your curve. Replacement times between 5 and 8 years. You can pause as you find this, but we see that the replacement time is approximately the percent that would have a replacement time between 5 and 8 years is 0.6721. And the last one, have a replacement time less than 5.1 or greater than 9.1. Here's where it's really important that you shade the areas described here. Go ahead and pause this as you try to sketch it out, and then use your technology to find it. Here's what your outcome should be. Notice that the word or is here. We're to the left of 5.1 and we're to the right of 9.1. That means we're in both tails and we have an or. So what we want is the sum of those two tails. One quick way to do this, instead of trying to find one tail and then adding the second tail, is to use the complement rule. If you go and do something kind of like we did up here and find the area between 5.1 and 9.1, that'll be the area in between. And if you find the complement of that, that'll find the area in your tails. So in other words, you would go 1 minus normal CDF, lower boundary 5.1, upper boundary 9.1. Find that, and 1 minus it is, you should get this value. Here's some more problems that you can work. This is dealing with midterm exams and normal distribution times. Our mean in this case is 73 and our standard deviation is 9 points. What's the probability a student chosen at random has a score between 80 and 90? Go ahead and calculate that. Actually, I'm going to lay all these out here. You can pause it, but when you come back, you can check your answers with what I have. So pause at this moment and see if you can sketch these out on a curve and find the probabilities. Also practice using probability notation if you haven't done so. Here are your answers. The probability that's between 80 and 90, we would read this as x is less than 90 and greater than 80. It's opening toward the x, so if we read it backwards, we need to actually use the opposite name for the symbol. It's less than symbol, but if we're reading it backwards, we say greater than. If we read it from left to right, this would be 80 is less than x, which is less than 90. regardless, here are the other results. Very good. Hopefully you've had some success with this, and you can feel confident in moving into some of the homework problems associated with the normal curve in section 8.4.